Hey folks, this is Dave Caudell on behalf of Dr. Berger's group at Fisk University, and I'm going to talk a little about AFM data analysis and a bit about the software I prefer called Gwyddion. Now, to illustrate the value of atomic force microscopy, let's take a look at some research we published concerning the use of indium iodide crystals for nuclear detection. We grew these crystals at Fisk, then fabricated radiation detectors out of them to see how well they could work. But this is a video about AFM analysis, so let's focus on that. To make the best detector possible, the surface of these crystals had to be very flat, down to the nanoscale, and this is where our AFM allows us to characterize and quantify how smooth the surface is. Each surface was polished in a method that uses alumina powder, with individual particles only a few hundred nanometers in size. To give you a sense of scale, the width of a human hair is roughly 100 microns, or 100,000 nanometers. This AFM image shows the surface of the crystal after it was polished, and it gives us a taste of how awesome this technology is. Under high magnification with a microscope, this surface was mirror smooth, yet in this image we can clearly see scratches along the surface that the particles left behind. In the lower right-hand corner of this image, we've also included the roughness and root mean square roughness, quantifying the surface of our crystal. Now our next image shows the same surface after we've used an etchant to eat away at the crystal. The surface is much smoother than before, and we've quantified this with our roughness measurements, which are half of what they were. So, let's move on to the software I use to analyze this data. And the software I'm going to introduce to you today is called Gwyddion. Now, Gwyddion is a multi-platform software for visualization and analysis of data from scanning probe microscopy techniques, such as the AFM images we just saw. It was developed by the Czech Metrology Institute. It's rated GPL, which stands for General Public License. This means that the software is free to use at no cost to you. And you can find it at gwyddion.net/download, or just simply Google Gwyddion, Gwyddion. Now, once you've installed Gwyddion, open the folder containing your data. You're looking for the files with topo near the end of their names. Topo stands for topography, and these are the files that contain the height data we're looking for. Go to Properties by right-clicking on the file, and click the Change button for Opens With. Browse the folders to where Gwyddion is installed. Then, select Gwyddion. In the future, you'll be able to automatically run Gwyddion by simply double-clicking on your data files. Now that Gwyddion is set as our default software, we can now just open up our folder that has our data inside. Remember not to use the tapping amplitude but the topography, and we can just simply double click on the one that we want to open, and it automatically runs some Gwyddion. Now this is a 2D representation of our height. I'm just going to go ahead and scale it up here so it's a little bit easier to see. The X and Y axis, which runs about 10 microns, or 10,000 nanometers, is our X and Y scale, and height, the Z scale, is represented by color. Now gray scale is the default. I'm not a big fan of that, so I'm going to right click here on the scale bar. I'm going to pick something I prefer, warm, and notice our scale goes from -0.44 to -0.08 microns. I'm going to right click on the data and say fix 0, which is going to set the lowest point at 0 and scale up from there. Now if we click this button over here, display 3D view of data, we have a little 3D image representation of our data, and we can manipulate it. The second icon here is going to scale the view as a whole, and then you just left click and drag, zoom in a little bit there. This also handles scale value if you want to exaggerate or minimize Z scale ratings. I'm not going to bother with that. I'm just going to switch back to the default tool. And one of the things we immediately notice is that this is a bit tilted. Now, I'm not a fan of grayscale, so I'm going to go ahead and switch this to warm as well. We can see that over 10,000 nanometers, we only have a rise of a few hundred nanometers. So it's fairly level, but it's not quite level enough because the features we're looking for are tens of nanometers, maybe less. So we need to level this out. And this is where the Gwyddion software is leaps and bounds ahead of the default software that comes with Bruker Nano. Bruker Nano used to be Vico. They used to have 3-point leveling, but for some reason in the later versions they don't anymore. But this software does. It's this little triangle icon here. It's called Level Data by Fitting a Plane Through 3 Points. And what it basically does is you choose 3 points that you know to be flat, and it will tilt your data to flatten it without actually altering any of the data itself. So I'm going to say apply, and we can immediately see here there's a lot of details that we didn't really see before. Notice our z-scale is a bit wonky again, so I'm going to again right click and say fix 0 to set the minimum value back to 0. And now we've only got a height variance of about 84 nanometers. Let me clear this and close it. So we go back to our height data. Now one of the things I immediately notice is that we've got a little bit of drift here in our piezoelectric motors. Let me bring this edge on so it's a little easier for you to see. All of this should be fairly flat. There are some little bits here that are actual features, but if you notice it drifts a little high and a little low, a little back high again. It's 10 microns is a pretty large range to be scanning, so the piezoelectric kind of drifts a little bit as it does. Now we can correct for that. You have to be careful with this correction. I know that this surface is mostly flat, so they should all be level. If you've got more of an amorphous surface, you can't do what I'm about to do. You got to make sure that you're doing this with flat. You come over to this icon. It says level rows using intersections with given lines. And then I'm going to draw a line over places that I can see are fairly flat. I'm avoiding little features and stuff like this. I always grab the top of this first line and drag it up to the very top. Now I don't want to hit any of these features, so I'm going to draw another one over here. Notice that I've got a little bit of overlap here. And I'm going to draw my third one down here. And I'm careful to avoid all these pits and stuff. And if I did this right, this should be nicely leveled. So I'll say apply. And one of the immediate things I notice is that I've got a bit of an artifact that's popped up here. And anything that's perfectly horizontal or perfectly vertical, you got to be wary of. There's a good chance that that's an artifact. And in this particular case, there was a little dimple right here that it leveled off that it wasn't supposed to, and so as a result, all this data to the left and right was raised up too high. So I'm going to drag this line back up here, above where this started. I'm going to start another one over here. Again, careful not to hit any bumps or divots and trying to align these. Now if I did this right, this line here should go away and everything should still be basically straight. So I'm going to click apply, and we see indeed that that was the case. So I'm going to clear this and close it. Again, I'm going to go ahead and fix 0. And now that we come over to our data, you can see it's fairly flat like it's supposed to be. What remains here are actual features on the material itself. So we've minimized the artifacts, and all we have left is the data that we were looking for. We've got slight little rises and stuff that might represent debris or junk on our calibration grading. I can also see here that there was a bit that was broken into. Maybe in a previous scan a tip got a little too rough. These triangular shapes, don't trust something that's symmetric in this particular case, because I believe these are bits of dust. This is caused by the tip was traveling too fast, and that's why these also have this triangular shape here. As the tip was traveling and it comes to a high and it starts to fall off, the tip is still traveling to the side as it's dropping, and so it's just measuring nothing until it hits a surface again, and that's what happens in each of these cases. That's why we end up with these triangular pieces. It's traveling and it's traveling and it finally hits something, and now it's traveling up along an actual feature. Okay, now if we're wanting to get the roughness or the root mean square of the roughness from our calibration grading or any other data that you're looking at, you come down here on Tools. For this part right here, this is Statistical Quantities, and it gives you a whole lot of stats. You can see this whole 10 by 10 micron area. It's giving a roughness, which is shown as this RA right here, of about 10.59 nanometers, and the root mean square of about 12.71 nanometers. Now if you're looking at a particular sample where you have like an artifact or something that's clearly throwing it off, like let's say we wanted to discount this large bit of dirt, but we find that this area over here is probably more representative, you can actually draw a box around it, and it'll give you a roughness of just what's inside that box. Now there are many more features I haven't touched on, but I'm trying to make this a brief video, so I'll end here. Once you start gathering your own data, I strongly encourage you to play around with the software. Thanks for watching.